Thank you for downloading this podcast from The Reedy Clubby Show on Talk Radio 702 and 567 Cape Talk. For more, please go to 702.co.za or capetalk.co.za. Talk Radio 702 and 567 Cape Talk. The Naked Scientist.
Ooh, Chris, I've got so many questions about this gene repair kit. First, tell us about it. What is this about?
Good morning, Reedy. Well, scientists are actually in a position now to begin to edit mistakes out of DNA. So DNA is our cell's recipe book. It tells our cells how to make the various things that make us work and keep us ticking over. But periodically, people crop up in the population who have mistakes in their DNA, genetic mutations, or as we age, our DNA acquires mutations or changes which can affect those recipes, and it's a bit like substituting salt for sugar in your cooking. The things that you cook up don't taste so good, and it means cells don't work so well in your body. What we'd like to be able to do is to go in there and fix those things. This might help. There's a paper, it's out in the journal eLife, by Jacob Giem Mikkelsen, who's a researcher at Aarhus University in Denmark. And what they've done is to take HIV, so the virus, and use it to infect cells, but it's a disabled or modified form of HIV, and when it goes into the cell, it delivers a certain set of proteins which are like little pairs of scissors that recognise specific sequences in the DNA in a cell. They then chop the DNA in various places to cut out the mistake, and then they take the genetic material, which is also packaged inside the virus particle, and they paste that into the DNA as the correct version of the DNA sequence. It's almost like a repair kit for a bicycle tyre, where you have a way of getting the inner tube out, you find the hole, you repair the damage and stick a plaster over it, and that's exactly what this does. So it means we've now got a way of editing DNA discreetly and safely and replacing damaged DNA sequence with healthy DNA sequence.
Okay, you have answered my question, because I wanted to ask when we use the term genetic mistakes, what are we referring to? You've said it's known as mutations, right?
Yeah, that's right. And this is part of how evolution works, because every time we reproduce, we pass on to our children between 30 and 50 new genetic changes or mutations. And in some respects, those are beneficial because they enable us to slowly change our genetic makeup and respond to pressures from the environment. But as we age, we also acquire these genetic changes, because when cells copy themselves or divide, they have to copy all 3 billion letters in their genetic code. And sometimes they make a spelling mistake. Sometimes those spelling mistakes don't matter, but sometimes they're in a critical place in the genome and they change the recipe in a way that can lead to all kinds of problems. And that means we need to be able to fix it.
All right. Thank you very much. And we go to the lines on 021 446 0567 011 883 0702. Is it Malcolm? Hi there.
Hi there, Reedy. How are you doing?
Very, very well. Thank you.
Good, thanks. Question for Chris. Chris, is it possible to create some sort of life form in a laboratory from a primitive sort of chemical soup or a mixture of chemicals?
Hello. Well, the answer, Malcolm, is no one's managed to make a life form that way yet. The closest we've come are in sort of 2 sets of experiments. One set of experiments were done in the 50s and 60s. And 70s, there was a gentleman called Stanley Miller who was working at University of California, San Diego, and he was interested in extending the work of Harold Urey, who came up with this idea that if you were to mix various chemicals together on the early Earth and then zap them with lightning and boil them up, eventually you'd make the building blocks of life. And what Stanley Miller did was to have an apparatus where he discharged a spark through some gases and boiled those gases up with a whole load of water, and did this for a long time. And he made all kinds of interesting chemicals in the laboratory, which only recently, because he died a decade ago or so, his colleague called Jeff Bader, also at University College San Diego, University of California, San Diego, he found a whole load of the original experiments put away in a box in the laboratory. And he fed those experiments into very modern analytical chemical equipment and discovered that what Stanley Miller thought he'd made was just a handful of chemicals. In fact, there were potentially tens or hundreds of different chemicals, all of which could be the early building blocks of life, made by these experiments which recreated the early environment on the early Earth. So on the one hand, we know that we can make complex chemicals which could contribute to the chemistry of life in an environment, in a laboratory, which does resemble what the Earth would have been like a few billion years ago. That's the first point. The second point is that more recently, Craig Venter, who you may know of as the gentleman who founded a company called Celera in California, and that company took on the NIH and the Wellcome Trust to be the race to sequence the human genome first. And they have various techniques for very quickly reading DNA. And they did read human DNA very, very quickly, but they've more recently gone in a slightly different direction and decided to see if they can make synthetic life. And about 4 years ago or so, they hit the headlines because they said, we have created an artificial bacterium. And what they were able to do was to make a genome, a synthetic genetic code, and then boot up a cell of a bug called a ureaplasma with this artificial genome. What they hadn't done was to make the cell get invented from first principles. They had to take a bacterium that already existed, get rid of its genetic material, and then put their new genome into it to boot it up. So therefore, what I'm presenting to you here is evidence that we can make cells work artificially, we can make the chemicals of life, but no one has yet managed to put the whole picture together and get the chemicals or the building blocks of life to make a cell, and that cell then boot itself up and operate. But that's what people are working on.
Thank you so much, Malcolm. Is it Scott in Durbanville? Hi there.
No, there. Perhaps I'm just probably it's a short one. What exactly is a virus? Because as I understand it, it's not really a living thing. It's not a bacteria. So what is the definition of it and its purpose?
Hello, Scott. You can think of a virus very simply as an infectious bag of genes. Viruses are tiny. They're an order of magnitude at least smaller, for the most part, than a bacterium. Mm-hmm. Bacteria are cells in their own right. They are independently living organisms that go about their business because they have everything in a bacterial cell they need to grow. A virus is an ultimate parasite. It's so tiny, it cannot do anything other than hijack another cell and use all of the machinery in that cell to make more viruses. And that's why I say it's an infectious bag of genes. And the role of a virus is merely to reproduce itself. And it does that by hijacking a cell. And even bacteria have viruses that prey on them. They're called bacteriophages. The virus goes inside the cell. It deploys its genetic material, which then shuts down all of the host cell's own genetic activity, and it turns the cell just into a machine for producing more virus particles. Each cell produces hundreds, if not thousands, of new virus particles which bud out from the infected cell, and then they go and infect other cells. And as they do so, they make genetic spelling mistakes, which means the virus can, under certain circumstances, evolve or change.
Thanks, Scott. Is it Faulkner in Simonstown?
That's me, yes.
Yes, go ahead, please.
I'd like to ask the naked scientist how it is that a whale can dive to great depths and not get the bends, because a whale is an air breather like we are. Okay, doke. Bye.
Hold on. Did you get that, Chris?
I did, yeah.
Okay,
So
how whales manage to go to great depths and not... Yeah. Okay.
Why don't whales get the bends but divers do? First of all, let's look at why do scuba divers get the bends. The reason a scuba diver gets the bends, if they don't dive judiciously, is that when you're going underwater, you're breathing compressed air, because for every 10 metres you go underwater, you gain an extra atmosphere of pressure on you. And this means that in order to be able to breathe, you need to breathe air at greater than the local pressure. So you're breathing air at a much higher pressure than you would breathe at the atmosphere, at the surface. And this means that the amount of gas that dissolves in your blood, in your tissue fluids and in your cells will be much higher, because if you put gas under pressure, it dissolves more easily than it otherwise would in water in the body. And that means that as you go down and down and down, the gas load in your body that's dissolved increases and increases and increases. It's held in solution, it's held dissolved by the pressure in the local environment. As you surface, the pressure drops again. If that gas isn't given time to re-equilibrate or come out of the tissues, out of your blood, and get back into a gas phase in your lungs and be breathed out, then it will form little bubbles in your blood, in your cells, and in your tissues. And we call that the bends. It's excruciatingly painful because it blocks blood vessels with little bubbles, and it causes tissue downstream of those areas supplied by those blood vessels to die. And people get bone lesions, you can have strokes and brain problems, and it can also rupture your lungs if you hold your breath when you're coming up because the volume of the gas expands. It's a bit like taking the top off a bottle of fizzy drink. It goes and out comes the gas. And so that's why divers surface slowly, and they also limit their time at depth because this limits the rate at which the gas can dissolve. Now, a whale, if you think about it, does not use scuba apparatus. When a whale dives, it's not breathing air from a tank. It's using just the air from the surface, which it has put into its bloodstream. It then often empties its lungs and then dives on empty lungs down to depth. So the whale does not take with it a huge cargo of extra gas and then top itself up. For this reason, there's only a limited amount of gas in solution in the whale's body, in its blood and in its tissues. And the whales also surface more slowly. So even though they have got gas dissolved out of their lungs, residual gas in their blood, the amount that's actually dissolved is limited. And because they're surfacing relatively slowly, it doesn't bubble out all at once, so they don't get the bends. If whales used scuba tanks, then they would.
And then Errol, you've been holding on for so long. Errol in Norwood, hi.
Okay, look, very quickly, there's a revolutionary development that is gaining momentum called 3D printing. Now, how on earth is it done? And secondly, there appears to be a research in this area for 3D printing of organs. And lastly, I just read recently in China, they built about 20 homes applying this principle in one day. I'll listen in the radio, okay?
Hi, Errol. Yes, you're right on the money with 3D printing. And funnily enough, talking about homes that can be 3D printed, the latest edition of the main Naked Scientist podcast, which you can get from our website, that's nakedscientist.com/podcast, we actually interviewed the people at DUS, DUS, DUS Architects in Amsterdam, who are 3D printing buildings in Amsterdam. They were one of the first people to start doing this, and they print the buildings room by room and then bolt them together, and you have a house. And it's a plastic house, and you can use all kinds of materials to 3D print your house, but they are printing houses in Amsterdam. Amazing stuff. Mm-hmm. What is 3D printing? Well, the idea here is that instead of just having a printer that spits some ink at a page to produce a page of text, why do we have to stop there? Why not feed the printer with something which it can melt, deposit, let congeal, and then build on top of that? And so you have these printers that take a model, basically you have a computer program that works out how to build things layer by layer, and then the printer deposits usually a plastic material or something that can be solid when it's cold and liquid when it's warm, and it deposits little splots or layers of this material and slowly builds up a three-dimensional version of whatever it is that you want to build. And these printers range from the kind of thing that sits on your desktop and can build little plastic objects right up to the massive scale, like the department, like the people I spoke to in Amsterdam who are building houses. Also, companies like Rolls-Royce, who do high-end manufacturing for jet engines and things, they're now using very similar techniques to 3D print components for engines for jets, and they do it by depositing little grains of metal, and then you zap them with a laser and fuse the metal together to make your alloy, and you slowly build complex objects up by doing these layer by layer deposition passes, and you can build engine components that might be in total a metre or more across that way.
Is it Mxolisi in Arcadia? Hi there, Mxolisi.
Hi, Reddy. I have a few questions, actually.
You know what? We don't have time for that. There are lots of people holding on. Can we do one for now?
Okay. I want to find out what the difference is between 95 petrol and 93 unleaded, and which is best for my car.
Okay.
Okay, well, those are the octane ratings. And when you make fuel is designed so that it has the optimal burn rate. In other words, when the piston comes up inside the cylinder, it's compressing the mixture of petrol and air in the cylinder. And as you compress air, you get something called adiabatic heating. It gets hotter. It's a bit like if you put your thumb over the hole on a bicycle pump and push the pump in hard, your thumb will get very hot because you're doing work against the air and it adiabatically heats. When you get to almost top dead centre, so the piston is almost at the top of the cylinder but not quite, the spark plug discharges a spark and this starts the fuel burning. And the idea is that then as the piston travels over the top, the burn then progresses so that it's at maximum rate as the piston is descending, and then you get your power stroke. You get the energy coming out of the burning fuel and the expansion of the gas transferred into the piston. Piston flies down, the engine takes that energy out and turns it into kinetic energy in the wheels. Car goes along. Now, in order to get that fuel to burn the right way, you need to have the right composition of fuel for a rate of compression in the engine and the size of the compression ratio in the engine. And 93 and 95 are slightly different grades of fuel that will burn in slightly different characteristic ways. And depending upon how the engine's set up, it will favour either the one that burns less easily or the one that burns a bit more easily. And that's what those numbers mean. They just vary the amount of branched chain alkanes in the fuel, and that changes its burning characteristic when it's in the engine.
Okay, Mxolisi, I'll tell you what, we've got your number. Next week we'll call you and give you a chance to ask the other question that you wanted to ask. We just want to give people a chance. People like David have been holding on for so long. David and Cyril Dean, hi.
Good morning to you. Good morning, Chris. Right, there is a plant called a castor oil plant, or the castor plant. Now tell me, how is it the plant itself is deadly poison? There's a poison that comes from that called ricin, for which there is no antidote, and yet the pharmacists produce castor oil. Now how come castor oil isn't a deadly poison, yet the plant from which it comes is very poisonous?
Hello, David. Yes, you're quite right. So the castor bean plant, if you get the seeds and the soft parts, you can extract a protein, which is called ricin, and ricin is a two-part toxin. It's basically two proteins stuck together. One of them takes the chemical to your cells, crowbars open a way into the cell, and then the other bit of it, its partner in crime if you like, slips inside the cell, and once it gets in there, it stops the cell's ability to make proteins. It stops the cell building its own polymers and things, and cells therefore break down. They stop working properly, and that's why it's toxic. The plants also in their beans produce a lot of oil, and that's because the oil is a very efficient way to store energy, and the plants use it as their energy store in their seeds. If you crush the seeds and get the oil out, but not the protein, because proteins don't mix very well with oil, then the oil is devoid of any of these toxins, and therefore it's completely safe.
Thank you very much, David. And is it Pius in Sunninghill? Hi.
Hi, Rudy. How are you?
Very well. Welcome. Your question?
Yeah, my question is, at the of human comatose, so the human body is in coma. And does the body...
sorry, Pius, is your radio on? Yes, it is.
Yes.
Okay, while you switch it off, let's go to Molefi in Troyville. Hi there, Molefi.
Hi, I just wanted to find out, how is it possible that every time I touch my girlfriend, her temperature feels relatively higher than mine? Doesn't matter where I'm touching her. I just feel colder than her. Is there a scientific reason to this?
Chris?
I love the choice of words. So some bits are warmer than others. So like your lips, for example, are warmer than your cheeks, as in your bum cheeks. It's quite a difficult one, this. My wife also always feels very hot, but swears blind she is cold. I'm not really sure what the answer is. I don't know if that's because there's a gross difference in body temperature between two individuals. I don't think there is. I think it's a subjective thing. Because we can touch ourselves in various places and think, oh, that's warm, but my hand feels cold. So I think it's probably that that basically your hands, being your peripheries, are slightly cooler than the rest of you. And where you touch people, if you touch people on the hand, then they might have warmer hands because they've been clasping their hands together, for example. But if you touch them elsewhere on their body, they're likely to be a bit warmer than their hands, so they might feel warmer. But that's a really rubbish answer, and I'm sorry. I don't know.
Okay. Keep touching, Molefi. Keep touching. Pius,
keep touching.
Pius in Sunninghill. Hi.
Hi, Rudy. Sorry about that.
No problem.
My question is, at the state of human comatose, so the body is in a coma state, and is it if the body metabolism does reduce at that time, is it possible that the replication of the viruses in the body, the rate of replication is also reduced? If that is possible, is that not the right time to apply medication to fight whatever virus in the body, especially the HIV virus?
Hello, Pius. So what you're saying is, when a person's in a coma, because their metabolism is reduced because they're in a coma, if their metabolism is reduced, then the rate at which viruses are growing in them should also be reduced, and this might be the right time to try to target a virus to combat it. You're on the right lines in the sense that because a virus is absolutely dependent on the cell it's living in to grow, if you slow down the rate at which cells can make raw materials available for a virus to use to grow, then the virus will grow more slowly. That's certainly true. But the problem is that you can't, you've got to inevitably at some point warm the person back up again and bring them out of their coma. So the virus would just speed up again afterwards. Also, many of the drugs that we use to combat viruses actually combat them by targeting their active growth or replication. There are a number of drugs which work by getting into the genetic material of the virus as it's trying to grow, and then they stop the genetic material growing properly. They stop the virus copying its genetic information. So if the virus isn't growing very fast, it will actually, therefore, not respond to the drugs very fast. So in fact, although the virus would grow slower when the person was in a coma, the treatments for many of these things wouldn't work so well. So actually we rely on the fast growth of a virus in order to get these drugs to work in the first place. So unfortunately, the strategy would be flawed.
Thanks, Pius. And there's an SMS here. Why do our eyes water when we yawn?
I think the reason for that is that when we yawn, you do two things. One, you squeeze your lacrimal gland, which makes tears a little tiny bit, by your facial muscle contortions as you go, like that. The other thing you do is you screw your eyes up. And when you screw your eyes up, you squeeze the duct which drains tears out of your eyes and into your nose, and you stop it draining the tears. So the tears continue to be produced into the eye, and in fact may be produced at a slightly higher rate because you've just squeezed your lacrimal gland, but the tears have got nowhere to go. So they overflow and come down your face, and that's why you cry when you yawn.
Chris, we'll see you again next week.
All right, thanks, Reedy. Take
Bye-bye.
care. Thanks,
Bye-bye.
everyone. Great questions.
Oh,
Bye-bye.
Lovely. I've really, really enjoyed it, and the feedback has been awesome as well. We'll podcast this conversation with the Naked Scientist, of course.